Good morning, guys. Today we're going to look at exponential functions, call them growth and decay problems. By the end of this video, hopefully you would be able to identify and explain different parts of an exponential function, excuse me, and you'd be able to write and evaluate an exponential function. Okay. So we should start off by looking at the general form of an exponential function graph, or an exponential function. I don't have to say graph. Okay. The variables that we're dealing with, same as usual, x and y. Okay. Notice them in their function. This is our exponential function here. Y equals a times b to the x. Okay. Then notice where x is. It's an exponent. Okay, and that's what makes this an exponential function. All right. The I guess constants that we'll have in the problem change depending on the problem, but for that problem are going to be the same. Our first one is a, and a is the initial value or starting value, and that's the value of where we're whatever the problem's talking about. We can talk about population or attendance or finances, but that's where it starts, and this value never equals 0. Okay, b is the growth or decay factor. B is the growth or decay factor, and that just shows how much it's increasing at that point. We'll talk about B. It's a little bit more complicated than just, or a little bit more involved than just one number, but we'll deal with that as we get there. Okay, if B is greater than 1, then the function is a growth function. That means it gets bigger over time. Okay, if B is less than 1, then the function is a decay factor. It means it gets smaller over time. Okay? And so we'll look at these things, being able to identify the initial value and the growth and decay in these examples down here. Remember, for examples, once you feel like you have a grip of it, pause it, and then see if you get the same answers as me. Or if you feel like you don't, or until that time, follow along with me as we do them. Alright, so initial value in this exponential function, we got y equals 12 times 1.05 to the x. Our initial value, remember we said that's a, here is 12. Okay, whatever we're talking about starts at 12. Is this a growth or decay function? Well, let's look at b. b is 1.05. Remember, our rule is if b is greater than 1, then it's a growth function. And if b is less than 1, it's a decay function. Here it's greater than 1. Okay? And my reasoning will either be b is greater than 1 or b is less than 1. b won't ever be 1. Okay? For an exponential function, if b was 1, that would just mean it's staying the same. 1 to any power is 1. Doesn't change anything. For 2, our initial value is 0.4. Okay? That's where a is. And it is a growth function because, again, b is greater than 1. It's 2. Okay. For our third example, our initial value is 5,000. Now look at b. b is a fraction, but 2/3 is still less than 1 now. So it's a decay value. It can be written as a fraction or decimal. Remember, those are really the same thing. They're interchangeable. And it's a decay value because, or decay function, because b is less than 1. Alright? So that's just being able to identify your different parts of the exponential function. So from there, we're going to try to be able to write and evaluate an exponential function given some information. So our first example says the population of a city is 50,000 and increases by 3% each year. Write an exponential function to represent the situation, and then tell how many people live in this city after 5 years. Okay, A, our initial value, deals with population. I know it's a number, but I'm just going to say deals with population here. Okay, our population is 50,000. B, our growth or decay function, our factor, is a 3% increase. Alright, now, like I said, B is a little bit more complicated than just being able to type 3 into a calculator or 3 into your function. So, I want you to think of having $100. Okay, and let's say you increase that $100 by 3%. How much money will you have? If, or we could use this situation, but we'll do with this. If you had $100 and I said you increased it by 3%, a lot of people would, in their calculator, you could say 100 times 3%, or 0.03 is a decimal. Okay, that'll give you $3. If you increased $100 by 3%, would you have $3? The answer is obviously in this situation, no. $3 wouldn't be an increase since you already had $100. So what we're going to do is, instead of, as we do our growth and decay factors, instead of just using the 3%, we need to say, well, it's growth. We have what we have, 100%, plus the 3%. Our growth rate is 1.03, okay? Okay, so 0.03 shows that it's actually decreasing by 93% or 97%. Okay, so when you do the growth rate or decay rate, you either add the growth rate to 1 or subtract it from 1. So your formula, if you want to think of it that way, is 1 plus r for growth and 1 minus r for decay. And it's up to you to figure out if the population or the whatever we're talking about is growing or shrinking. Now, let me take this calculator down. Alright, so the previous example, we had a population of 50,000 and we had a growth factor of 1.03, okay, 1 plus 0.03. So the exponential function should look like this. Y equals 50,000, that initial value, times 1.03 to the x. Okay, and it says the population after 5 years, so x is the time, y stands for our population. If we do that in a calculator, I'll do that in this calculator. I'll try to keep my order of operations, so I'm going to do the exponent first to the 5th, okay, times 50,000. Okay, and that would be 57,963, I'll say 0.7. Okay, probably rounded up to 0.4 in a problem, but that's what I got on the calculator for right now. Alright, so again, if you can, pause it and try to do these without me. I'll go through these a little bit quicker without as much step-by-step. Well, I guess I'll still do step-by-step, but I'll go through these quicker. Alright, car initially cost $20,000. It depreciates 16% each year. Write an exponential function. So I have y equals our initial value, 20,000, times, and this is going to be 1 minus 0.16. Depreciates, so it gets smaller. And then we want to find the value after 7 years, so that's my time up here. So I'll do 0.84 to the 7th first, so I can have that down, times 20,000. And so that means after 7 years, do that right, it's $5,901. Make sure I did that right, 1 minus 16. Nope. 15. Okay, so that's 0.84 to the 7 times 20,000. Alright, there we go. And 80 cents. I'll say 81 cents. Alright. After 15 years, the buyer decides to sell the car for $3,000. Is that a fair price? Okay, so what's changed in this situation? Nothing else. It still depreciates 16% a year. Is the time. So I'm just going to change this function, 0.84 to the 15th. Okay, so 0.84 to the 15th times 20,000. And that says y should equal $1,462.92. Okay? So if somebody tried to sell me this car 15 years down the road for $3,000, they're overcharging me. Okay, it's only worth $1,462.92. Sure, if they want to get the cents out of me, I'd pay that, but not $3,000. Okay. All right. On your own, I'd like for you to bring this problem completed into class. I'll help you out with the function. Movie, I remember seeing it once. Pay it forward. The guy wants to make sure that he did a nice thing for 3 people. One person did a nice thing for 3 people, and he wanted them to pay it forward by doing that nice thing to 3 more people. And so, the function for this, y equals, we got one person, and he did a nice thing for 3 people. So he increased, and he wanted those 3 people to do a nice thing for 3 more people. He wanted a 300% increase on his good deed. Okay. And we'll just say to the x because we don't have a time or anything written for that. Okay. All right. For me, I'll check this on Monday. Bring these 3 solutions. All right. Have a great weekend.